and formulas for lengths. If one or both the surfaces of the transparent medium are spherical, it is called lengths. If the distance between two spherical surfaces of lengths is very small compared to radii of curvature of its two spherical surfaces, a length is called thin length. Lengths maker and Gaussian formulas for thin lengths. A point-like source of light O is arranged on the principal axis P, P' on the lens thickness L. C1 is the center of curvature of the convex surface facing the object O. A ray of light emerging from O in the direction making an angle alpha with the axis is incident at point Q on the convex surface of the lens. It is refracted there and then proceeds along the straight line in direction Q, Q' and arrives at point Q' on the other surface of the lens. It is refracted again at Q' and moves along Q'I direction. Another ray of light from O moving along the principal axis is incident at right angle to both the surfaces. Hence, without suffering any deviation, it meets the ray Q'I and forms the image of O at point I. Object distance OP is equal to DO. The virtual image distance P'I is equal to DI. Radius of curvature of two surfaces of the lens are C1, P is equal to R1 and C2 P' is equal to R2, and thickness of the lens P' is equal to L. The object is situated in the air, therefore N1 is equal to 1. If the refractive index of the material of lens is denoted by N, then N2 is equal to N and R is equal to R1 for the first surface. The image is on the virtual side, hence the image distance is equal to minus DI. Substituting these values in equation, we get (1 upon DO minus N upon DI is equal to N minus 1 upon R1. The image I formed due to the refraction at the first surface acts as real object for the second surface of the lens. Thus, for the second surface of the lens, object distance D-O is equal to DI plus L. Image distance will be DI and the ray enters the air from glass. Thus, we have N1 is equal to N and N2 is equal to 1 in this case. Radius of curvature of the second surface of the lens is R2. Thus, R is equal to R2. Substituting these values in equation, N upon D-O plus 1 upon DI is equal to 1 minus N upon R2. Therefore, N upon DI plus L plus 1 upon DI is equal to minus N minus 1 upon R2. Thickness L of thin lens being very small compared to DI, we ignore L in equation. n upon di plus 1 upon di is equal to minus n minus 1 upon r2. Adding equations, one upon do plus 1 upon di is equal to n minus 1 into 1 upon r1 minus 1 upon r2. Now, if we take the object at infinite distance, then the parallel rays of light coming from it will be refracted by the lens. An image is formed at the principal focus of the lens. Thus, when DO is equal to infinite, DI is equal to focal length f. Substituting these values of DO and DI in equation, one upon f is equal to n minus 1, 1 upon r1 minus 1 upon r2. This equation is known as lens-maker formula. Combining equations, one upon DO plus 1 upon DI is equal to 1 upon f. This equation shows the relationship between DO, DI and f for thin lens. It is known as Gaussian formula for the lens. Same equation exists for concave lens also. The formula for the magnification by lens can be also obtained in the same way adopted for mirrors, which is m is equal to minus di upon do. Example, what should be the value of the radius of curvature to prepare a convex lenses from the material of refractive index 1.5, having equal radii of curvature and focal length of 0.20 meters. Here, n is equal to 1.5, f is equal to 0.20 meters, r1 is equal to r2 is equal to r is equal to, using lens-maker formula, 1 upon 0.20 is equal to 1.5 minus 1, 1 upon r plus 1 upon r. Therefore, r is equal to 0.2 meters.